Okay, in this video I will continue to talk about the interaction of spin magnetic moments. My aim is to determine the eigenvalues and the eigenfunctions for such systems. Hence, let us consider two magnetic moments μ1 and μ2 separated by distance r in magnetic field B. The expression for magnetic interactions energy of such system includes scalar products μ1b and μ2b describing the interaction of magnetic moments with magnetic field B, and a term describing the magnetic dipolar interaction between two magnetic moments, which I have discussed in my previous video. The link to this video is given in the description. Further, I will substitute the vectors μ1 and μ2 in the above expression for energy by the corresponding magnetic moment operators, which are proportional to angular spin momentum operators h bar s1 and h bar s2, respectively. The proportionality coefficients gamma 1 and gamma 2 in the last relations are the gyromagnetic ratio for the first and the second particle spin, respectively. This gives us a spin Hamiltonian which has the following form, which is very similar to the above expression for energy. Okay, in order to utilize this Hamiltonian in the following derivations, it is transformed. First of all, we introduce a coordinate system oriented along the magnetic field B. In this coordinate system, the vector B will have just one component, Bz. Further, we express the distance vector r via its absolute value and via the polar angle theta and the azimuth angle phi. This allows me to write the spin Hamiltonian divided by h bar as follows. The scalar products of Zeeman interactions are simplified to the terms proportional just to Sz operators. And the term originating from the dipole-dipole interaction is presented as a sum of 6 operators A, B, C, D, E, and F. Here the terms A and B do not depend on the angle phi and are given by the following formula. Just to remind, the angle theta is the angle between the distance vector r and the magnetic field B as shown at the figure. The term C is proportional to the exponential function of minus I phi, and the operator D is the complex conjugated of the operator C, which means it is proportional to the exponent of I phi. Similarly, the operator E is proportional to the exponential function of minus 2I phi, and the operator F is the complex conjugated operator E, which means it is proportional to the exponent of 2I phi. Just to remind, the constant d dip, which was introduced here, is proportional to the other constants, μ0, gamma 1, gamma 2, and h bar. Okay, we obtained this Hamiltonian, which can be used to determine eigenfunction and eigenstates. Now, I would like to make some comments about the usage of this Hamiltonian expression. The question is, can the energy levels which are obtained from this Hamiltonian be used to determine spectral line frequency and spectral sheen for some realistic spin system? For example, can we take this Hamiltonian to describe a water NMR spectra? As we know, water molecule has two protons with spin 1/2 and corresponding magnetic moments which are dipolar coupled. What will be if we put a water sample into an NMR spectrometer and measure a spectrum? Will the measured spectrum coincide with those calculated from the Hamiltonian above? The answer is the coincidence will not be very good. There are other factors which needs to be taken into account in order to agree with the experimental data. For such system, we need to make the model more sophisticated. For example, the water molecular motion, which leads to fast variation of spin-dipolar interaction, needs to be counted. Also, we need to include into the model interaction of water protein from different molecules. Despite all this imperfection, the determination of eigenvalues and eigenfunction of the above Hamiltonian can help us greatly to understand more complicated systems. Hence, we will focus now on the solution of the eigenvalues and eigenstates problem for the above Hamiltonian. Okay, how can it be done? The first approach, which can be made here, is to determine energy levels numerically. If we have two spin-1/2 particles, then the operator S1z and S2z are 4x4 matrices obtained by the tensor multiplication. S1z is the product of the usual spin-1/2 SZ operator with a unit 2x2 matrix, and S2z is a product of a unit 2x2 matrix with a usual spin-1/2 SZ projection operator. Further, we can choose some values of field B, distance r, and angles theta and phi, and plug all these parameters into the formula for the Hamiltonian in order to set its numerical value. If we have a numerical value for the Hamiltonian matrix, we can use a computer to determine its eigenvalues and eigenvectors. In this way, the energy levels and the wave function of our spin Hamiltonian can be determined numerically. Of course, a numerical solution is good. However, it's not so well suited to understanding the role of all parameters which enter the Hamiltonian and further prediction of the system behavior as an analytical solution is. In this specific case of the system consisting of two spin-1/2 particles, we can try to derive analytical expression for the energy levels and wave function. However, this expression will be so large and cumbersome that it would be barely possible to get some advantage out of them. Another approach is to make some Hamiltonian simplification which allow us to obtain some vivid solution for the energy levels and wave function, and later clarify how this solution is suited to describe behavior of real spin systems. One of such simplification is to preserve just one term in the spin-dipolar interaction Hamiltonian, namely the term A. Hence, we arrive at the Hamiltonian, which consists of Zeeman interaction of both spins with the magnetic field B, and the spin-dipolar interaction term, which is obtained by omitting B, C, D, E, and F operator in the curled parentheses in the Hamilton expression above. Okay, let us consider the derived Hamiltonian. For convenience, I introduce the cyclic frequencies omega 1 equal to minus gamma 1b and omega 2 equal to minus gamma 2b. Also, I define the dipolar frequency omega d equal to d divided by r cubed and multiplied by 1 minus 3 cosine squared theta. With this definition, we can rewrite the Hamiltonian in a compact form. If I insert in this expression the S1z operator and S2z operator shown above, I will get a diagonal 4x4 matrix. The diagonal elements of this matrix are omega plus omega d divided by 4, delta omega divided by 2 minus omega d divided by 4 minus delta omega divided by 2 minus omega d divided by 4, and the last one minus omega plus omega d divided by 4. The frequency omega is the average frequency of omega 1 and omega 2, and the variable delta omega is the difference between omega 1 and omega 2. The eigenvalues of the matrix H are its diagonal elements. Also, it is very easy to determine the eigenvectors of this matrix. Simply, they coincide with the standard basis unit vectors and are given by the formulas. If we remind ourselves that the eigenvectors of the spinel half as that projection operator are 1, 0 and 0, 1, sometimes called spin up and spin down, then the eigenvectors of the H operators E1, E2, E3 and E4 can be expressed as the tensor products of spin up and spin down vectors. Hence, we have obtained 4 eigenvalues and 4 eigenvectors for the Hamilton operator H in a rather simple form. Based on these results, I would like to point out an important case, that is, when gamma 1 is equal to gamma 2. In this situation, we have omega 1 equal to omega 2 and delta omega equal to 0. Also, we are left only with 3 different eigenvalues: omega plus omega d divided by 4, minus omega d divided by 4, and minus omega plus omega d divided by 4. Remarkably, the situation when gamma 1 is equal to gamma 2 corresponds to the case when we have two identical particles. In this case, the wave function of the spin system needs to be symmetric or antisymmetric. The wave function or eigenvectors E1 and E4 are already symmetric. The eigenvectors E2 and E3 are not symmetric or antisymmetric with respect to the exchange of the particle variables. However, E2 and E3 eigenvectors correspond to the same eigenvalues, and therefore any linear combination of these two vectors will also be an eigenvector of the Hamiltonian H. Therefore, I can write the symmetrized eigenvectors of the Hamiltonian H as t plus equal to spin up, t0 is equal to 1 over square root of 2, spin up, spin down plus spin down, spin up, s0 equal to 1 over square root of 2, spin up, spin down minus spin down, spin up, and t minus equal to spin down, spin down. As you can see, t plus, t0 and t minus are symmetric and correspond to the triplet state, and S0 is the antisymmetric eigenvector and corresponds to the singlet state. Okay, let us analyze the dependence of energy levels on magnetic field B by plotting the obtained eigenvalues as a function of B. Here I will consider the case when the frequency omega 1 is larger than the frequency omega 2 and larger than 0, which corresponds to the situation when gamma 1 is smaller than gamma 2 and smaller than 0. Okay, let's do this plot. Along the vertical omega axis we have two important points. The first is minus omega d divided by 4, where two eigenvalues, the second and the third, meet at zero magnetic field. And the second point is omega d divided by 4, where another two eigenvalues, the first and the fourth, meet at zero magnetic field. Using these points, I can plot all four eigenvalues of the spin Hamiltonian, which linearly depend on the magnetic field B, as shown at the plot. Here I will also indicate the transition between the first and the second energy level, which corresponds to the inversion of the second spin. The frequency of this transition is equal to omega 2 plus omega d divided by 2. Additionally, I indicate the transition between the third and the fourth energy levels, which also corresponds to the inversion of the second spin, but in this case with the frequency omega 2 minus omega d divided by 2. Similarly, other transition can be illustrated with this plot. At the end, I can assign to each energy level its spin configuration. Okay, we have successfully found the eigenvalues and eigenfunction for a very simple dipolar interaction Hamiltonian. Now let's try to consider a little bit more complicated dipolar interaction Hamiltonian. I will take now besides the A term from dipolar alphabet also the B term. Explicitly this gives me the following expression, which in comparison to the previous case has a flip-flop term given by the operator S1 plus S2 minus plus S1 minus S2 plus. Remarkably, the two eigenvectors T plus and T minus which we have obtained for the simpler Hamiltonian above are also the eigenvectors for this Hamiltonian. They give us the eigenvalues omega plus omega d divided by 4 and minus omega plus omega d divided by 4 respectively. The other two eigenvectors are searched in the form of a linear combination of a triplet state T0 and a singlet state S0, which are orthogonal to the states T plus and T minus. For this purpose, we need to solve the equation H multiplied by the linear combination x T0 plus y S0 is equal to some eigenvalues omega multiplies with the same linear combination x T0 plus y S0. In other words, we need to determine parameter x, y, and omega which satisfies this equation. Just to remind, T0 and S0 are given by these expressions. Now I will rewrite the equation for eigenvalues and eigenvectors in the explicit form. For this purpose, I will need the following auxiliary formulas. I will skip the comments of these formulas since they can be easily verified by simple and direct calculation of spin operator action on the spin states T0 and S0. Now, by inserting our Hamilton operator into the equation for the eigenvalues and eigenstates, and using their formulas, I obtain the following equation. This equation can be satisfied if the sum of all terms proportional to T0 is equal to 0, and the sum of all the terms containing S0 also equal to 0. This gives us two equations. The first is minus capital omega minus omega d divided by 2 multiplied by x plus delta omega divided by 2 y is equal to 0. And the second one is delta omega divided by 2x minus capital omega y is equal to 0. This system of the two linear equations has a solution when the determinant of the system matrix is equal to 0. That is, the last determinant in the explicit form gives us a quadratic equation for the eigenvalues. It has two solutions. Omega A is equal to minus omega d divided by 4 minus omega stroke divided by 4 and omega B equal to minus omega d divided by 4 plus omega stroke divided by 4. Here I introduced a new variable omega stroke, which is the square root of omega d squared plus 4 delta omega squared. Now, in order to determine parameters xa and ya, which corresponds to the eigenvalues omega a, we insert omega a in the system of two linear equations shown above. Such steps give us basically one relation: ya is equal to minus delta omega divided by 2, 1 over absolute value of omega a multiplied by xa. Similarly, to determine parameters xb and yb, which corresponds to the eigenvalue omega b, we insert omega b in the system of linear equations. In this way, we obtain the relation xb is equal to delta omega divided by 2, 1 over the absolute value of omega a multiplied by yb. Please note that in the last relation we have again omega a. Further, I will use the normalization condition for the wave function. In our case, it means that the square root of xa squared plus ya squared is equal to 1. By inserting the relation linking ya to xa into this normalization condition, we obtain the expression for xy and ya. Here I have introduced a new variable, capital omega star, which is equal to the square root of 2 omega a squared plus delta omega squared. Similarly, I can use the normalization condition for the second wave function, which is determined by the parameters xb and yb. By inserting these relations between xb and yb into the normalization condition, we obtain the following expression for xb and yb. xb is equal to delta omega divided by omega star, and yb is equal to 2 omega a absolute value divided by omega star. It is convenient to introduce the angle phi, while the relation cosine phi is equal to 2 absolute value omega a divided by omega star. Consequently, sinus phi is equal to delta omega divided by omega star. Hence, we can write down all four eigenvalues of our spin Hamiltonian. Omega 1 bar is equal to omega plus omega d divided by 4. Omega 2 bar is equal to minus omega d divided by 4 plus omega stroke divided by 4. Omega 3 bar is equal to minus omega d divided by 4 minus omega stroke divided by 4. And the last one, omega 4 bar is equal to minus omega plus omega d divided by 4. Also, we have four eigenvectors which correspond to these eigenvalues. They are t plus sinus phi t0 plus cosinus phi s0, cosinus phi t0 minus sinus phi s0, and t minus. Here I will just briefly remind you that t0 and s0 are given by the following expressions. Having obtained a rather general result for eigenvalues and eigenvectors, it is interesting to consider some special cases. The first case is when the gyromagnetic ratio of both spins gamma 1 and gamma 2 are equal. It gives us delta omega equal to 0. Also, it follows immediately from the definition of sinus phi that it is equal to 0, and consequently cosine phi is equal to 1. With these remarks, we can easily obtain a new set of four eigenvalues for our special case. It is easy to see that they are obtained when the variable omega stroke in the general expression for eigenvalues is substituted just with omega d. Also, we can easily obtain eigenvectors for this case. Here, psi1, psi3, and psi4 are the wave function of the triplet state. Psi2 is the singlet state. This result is also easily obtained if we put sin phi equals 0 and cosine phi equals 1 in the general expression for the eigenvectors shown above. Now we consider the second special case when delta omega is much larger than omega d. From this condition, it follows that cosine phi is equal to sin phi and equal to 1 over square root of 2. The case when delta omega is much larger than omega d is sometimes called the weak coupling limit. Similarly, as in the previous case, we obtain the eigenvalues from the general expression for the eigenvalues by substituting the variable omega stroke just with delta omega. In this way, we obtain now if I insert 1 over square root of 2 instead of cosine phi and sin phi in the general expression for the eigenvectors, I will obtain the following eigenvectors in the weak coupling limit. Now, if we compare the obtained results for eigenvalues and eigenvectors in the weak coupling limit to the result for eigenfunction and eigenvalues, which we have obtained considering just a term in the dipolar interaction Hamiltonian, we will see that they are the same. Hence, we can conclude that accounting for an additional term proportional to the operator B in the dipolar interaction Hamiltonian did not affect eigenvectors and eigenvalues in the weak coupling limit. However, the term B, or the flip-flop term in the dipolar interaction Hamiltonian, has changed the eigenvalues and eigenvectors in the case when delta omega is equal to 0. Now we can determine the transition frequency between the energy levels of our two spin 1/2 system. First, we consider the case delta omega equals 0 and determine the transition frequency between the triplet states. The transition frequency from the first to the third energy level, omega 1,3, is equal to omega 1 bar minus omega 3 bar, which is equal to omega plus 3/4 omega d. The transition frequency between the third and the fourth energy level, omega 3, 4, is equal to omega 3 bar minus omega 4 bar, which is equal to omega minus 3/4 omega d. Summarizing these two expressions into one formula, we obtain that the transition frequency of one of the two lines, delta omega with wave, is equal to omega plus minus 3/4 omega d. Now we consider the case of weak coupling. The transition frequency between the first and the second energy level is equal to omega 2 plus omega d divided by 2, and the transition frequency between the third and the fourth energy level is equal to omega 2 minus omega d divided by 2. This two transition corresponds to the situation when the first spin orientation is fixed and the second spin is inverted. For the frequency of these two lines, we can write a generalized formula. Delta omega with wave is equal to omega 2 plus minus omega d divided by 2. Similarly, we can handle the situation when the orientation of the second spin is fixed, but the first spin is inverted. The transition frequency of these two lines can be written as delta omega with the wave is equal to omega 1 plus minus omega d divided by 2. Okay, now we will consider dependence of energy levels or eigenvalues of our spin Hamiltonian on magnetic field B. As the example, I will take the limit of strong coupling and plot the eigenfrequency of our spin Hamiltonian as function of magnetic field B. Okay, let's start with the zero magnetic field. Here, along the omega axis, we have three important points. 0 is the energy of the singlet state, omega d divided by 4 is the energy of the first and the fourth state, and minus d divided by 2 is the energy of the triplet state T0. As the magnetic field B increases, the energy gap between the triplet state spin up, and spin down increase linearly, as shown in the plot. Here I would like to remind that I consider the case when omega 1 is larger than omega 2 and larger than 0, and also the difference omega 1 minus omega 2 is much smaller than omega d. In this case, the eigenfrequency of the triplet state T0 remains close to minus omega d divided by 2, and the energy of the singlet state as 0 remains close to 0. To denote the eigenfrequency of the last two states S0 and T0, I have written the exact formulas for the eigenvalues, which contain variable delta omega, which in this case should be very small. The purpose of preserving delta omega in this formula is to show that the neglection of delta omega is only possible for low fields. If the magnetic field B is increased very much, then delta omega will become very large and the strong coupling limit will not be valid anymore. Okay, we can also here indicate the wave function or eigenvectors of the spin Hamiltonian for each energy level. Also, I would like to indicate here the transition between the triplet state 1, 3 and 3, 4. As I already explained, these two transitions are responsible for two spectral lines with the frequency omega plus minus 3/4 omega d. It is important to mention that the frequency omega d in our system depends on distance r and angle theta and is given by the formula d deep divided by r cubed and multiplied by 1 minus 3 cosine square theta. Hence, the two frequency of the two lines corresponding to the transition between level 1 and 3 and level 3 and 4 respectively are given by the formula delta omega is equal to omega plus minus 3/4 d deep divided by r cubed multiplied by 1 minus 3 cosine squared theta. Regarding this result, I would like to mention that there is another my video where I calculate the spectral shape for an ensemble of systems or molecules which can emit the photons with such frequencies, as given by the formula for delta omega. The topic of this video is Pake pattern or Pake doublet, and the link to it is given in the description to this video. Here I would like to make another comment related to the transition between the energy levels. Generally, a transition between any two levels shown in this diagram can be imagined. For example, between levels 2 and 3, or 1 or 4. However, this transition can be forbidden or happen with a very low probability. A detailed analysis for the transition probability can be a topic for a new video lecture and is going beyond the scope of this presentation. Okay, now I would like to summarize the results. In this video, I was explaining how to find eigenvectors and eigenvalues for this spin Hamiltonian, which can describe two spins in external magnetic field with dipolar interaction between spin magnetic moments. Since numerical or general analytical solutions are not very suitable for analysis, I have started solution of this problem by truncating the dipolar interaction Hamiltonian to just one term A. Later I have added the second term B into the consideration. It was shown that the term B did not change the eigenvalues and eigenvectors in the weak coupling limits. However, the term B was important in the case when the gyromagnetic ratio gamma 1 and gamma 2 are equal. Now the question is, what is about the other terms C, D, E, and F? Obviously, adding them into the consideration will further complicate the computation and calculation of eigenvectors and eigenvalues. However, it can be shown that their effect on the eigenvectors and eigenvalues is very small under usual experimental conditions. More often, they play a role when relaxation processes are described. With this, I would like to finish and thank you for watching this video. Bye.